И мы завершаем первый день хардкорного трека докладом Моники Beckwith. Я очень рад, что Моника Beckwith согласилась участвовать в нашей конференции So No One, потому что Моника настоящий эксперт в области GC. И это очень круто, что она согласилась принять участие. Как и многим известный Алексей Шепелев, Моника работала в команде перформанс-инженеров, сначала сам, потом Oracle, но ей приходилось разгонять именно сборщики мусора, и в частности J1, сборщик мусора, и поэтому J1 она знает просто вдоль и поперек. Но сегодня она расскажет про совсем новый сборщик мусора, который появился совсем недавно, ZGC, и это абсолютный эксклюзив, этот доклад Моника представит в первый раз. Почему ZGC? Потому что low pauses, и время такое, что паузы никому не нужны. Итак, Моника Beckwith. Hi, Monica.
Hi, everyone.
Hi.
Hi. Yeah.
G1 is a default GC in OpenJDK today, and it became default not so long time ago, and you are the person who made it possible. I know that you made many efforts to make it default, and that GC is very young. And do you think that there are chances for low pauses GCs to become default someday? Because you know that the low pauses GCs has some performance overheads.
Yeah, so I think that's a great question. A default means that it's applicable to most of the workloads, not all the workloads, but most of the workloads. If you remember the first time the default was serial GC, then we moved to parallel GC, and then we're moving to low latency collectors. So the whole study of what becomes a default becomes it's on the workloads that are currently there. So once the
Хорошо. Окей. Небольшие технические неувязки, в которые мы сейчас наверняка справимся. Но сейчас осталось нам совсем немного. Я думаю, что все будет хорошо. Моника к нам вернется и представит нам действительно совершенно новый доклад. ZGC — это хорошо. Особенно в больших проектах, где паузы совсем не нужны. Осталось совсем маленько. Ну, да, вот так бывает, что конференция онлайн, человек далеко, может пропасть неожиданно с экранов телевизора. Я еще сейчас буду немножко держать время, ваше внимание. Да, буду пытаться дальше держать внимание. Что еще можно про Монику интересного рассказать? Да, мы сейчас говорили перед этим ее выступлением про то, что делается в Microsoft. То есть она сейчас работает в Microsoft, раньше она работала в Oracle или в Sun. У них сейчас она тоже занимается разгоном производительности в Microsoft. Да, у Microsoft сейчас есть Azure, там есть Java. Кроме того, у них есть Windows, которым должна быть Java. И кроме того, у них есть Windows на ARM64, которая тоже должна быть Java. И как раз команда Моники недавно портировала OpenJDK на Windows ARM64 успешно, и скоро он запустится. И можно будет еще и запускать ваше приложение не только в Linux, но и в Windows, и не только на интеловских процессорах, но еще и на армовских процессорах тоже, что, наверное, совсем даже, тоже имеет какой-то смысл, я так думаю. Вот. И да, у них команда, у них вроде бы не очень большая VM-ная, но у них очень много про Java сейчас в инфраструктуре, до сотни человек там доходит, которые инфраструктурой Java занимается, что тоже, то есть Microsoft тоже Java любит, и это хорошо, и забирает довольно неплохих инженеров к себе в проекты. даже очень хороших инженеров. Что у нас там еще? Не полечилось ничего, ребята? Похоже, еще ничего не полечилось. Да, ну... Неожиданно, конечно, да. А? Давайте, хорошо. Про что же еще рассказать? Ну да. Hi, Monica.
Hi,
Can you hear me?
Yes, I can.
Yes, and but you can't share your slides still, right?
I shared my slides. Do you not see them? Just a second.
No, don't. Oh, okay, great. So now we can start.
Okay.
Please start, Monica.
Okay. Yes, thank you. Yes.
Can
thank you, Nikita.
can you make it full screen, please?
Oh, okay. Just a second. Let me close this. Okay. Yes. Maybe.
We see your speaker notes with, instead of your presentations.
Yes. Yeah. Let me just give me a second, please. I apologize. Okay.
Okay. And now Monica tries to...
So So let me start while the Zoom is connecting. Today I want to cover ZGC, and I want to talk more about what makes it different, like the whole concurrent compaction stuff that is introduced by this newer low latency collector. And I want to also share some numbers. So what I've done is I have I've compared ZGC with G1 GC to show how GC tries to maintain these low sub-millisecond pause times. I'm sorry, my Zoom is updating right now for some reason. So I'm going to kill, yes, exactly. I'm going to kill the program and I'm going to start that again here while I can continue talking to the presentation that you will shortly see. Okay. So basically I have used two benchmarks for presentation. One is called the heap fragger. If people that have, it looks like I'm online now. I'm going to share the screen here. And here we go. PowerPoint slides, and this should share right now. Let me know if you're able to see my slides.
No, Oh, great.
Yes.
So let's
okay.
Start
awesome.
Now.
So yes. So I was talking about the basically I'll go and talk about what makes ZGC different than other garbage collectors, and then the performance impact and the comparison with G1. So let's dive in. So the way I want to start is talk about how to design a garbage collector and what makes the evolution of garbage collectors in OpenJDK Hotspot especially. Okay. So one of the things that we have seen in OpenJDK Hotspot that generational collectors do really well, and that's because it's based on the longevity of object principle. Basically, how long does an object live? And the general consensus is that most objects die young. So as soon as you allocate, they do some transactions and they are dead already. So there's a whole concept of live data set, which I have used in this slide deck, even for my performance comparison. So the short form for live data set is LDS. So you will see LDS mentioned multiple times in the slide. Having generational is to build up that LDS in your old generation, right? The second concept is that if your GC work can be done by multiple threads, then that also helps to finish the work early. So it doesn't matter, many of the GCs you'll see as concurrent GCs, but even the work can be done in parallel. And similarly, for stop the world, it's even better if you have parallel threads working to kind of complete the work. So there's task stealing, and there is the distribution and notifications and handling of there's also this concept of thread local handshakes, where you don't need a global stop the world pause. But I will talk more about that as I go and explain these. So with those two, let's design a basic garbage collector. So as I mentioned, one of the basic concepts with all garbage collectors until G1 GC
Да, мы дико извиняемся, конечно, что такое происходит. Ну да, Моника находится в США, в Техасе, и да, в США не везде хороший интернет, к сожалению, и с этим сложно что-то поделать. Вот вернулись, ура. Monica, can you hear us? We can't hear you. We now only see the slides and can't hear Monica. Unfortunately, да, я, к сожалению, не видел этого доклада, потому что он совершенно новый, поэтому мне сложно комментировать, но как мы видим, да, мы здесь пытаемся задизайнить JC. Был у нас сначала generational гипотеза, но с ней есть проблемы, что она плохо параллелится. Теперь мы пытаемся распараллелить. И ура! Мы можем либо stop the world либо делать это все одновременно с нашими потоками. Да, я вижу. Но что говорит сейчас конкретно Моника, я не знаю, поэтому да, есть такие проблемы у нас. Да, здесь барьеры, да, у нас, как вы видите, у нас проблема с Generational GC, что нам нужно отслеживать ссылки между старым и новым поколением. И это довольно-таки интересная задача, которая тоже довольно непонятно, как параллелить. Хотя, понятное дело, что зато мы можем быстро собирать на молодое поколение очень быстро. Но если у нас вдруг случается, что все скопилось в старом поколении, тут начинаются проблемы.
Hello.
Oh, Monica, you're back again.
Sorry. Yes. So I'm not sure where we lost, but I'm keeping this window open right next to me, okay? So I was talking about generational collector and parallel work that can be done in either the pause itself or the concurrent threads, which also can be in parallel. So with the concurrent threads, we need to have maintenance barriers as well, because remember, the concurrent threads of the garbage collector are actually working with your application threads, also known as the mutators, okay? And so now, with the simple garbage collector that we just designed, we want to make sure that we can maximize the throughput, right? So what that means, we want to avoid fragmentation, and we also do not want to take the resources away from the application. Because as soon as you make your applications, for example, the CPU time that you're using for your application, if you employ background threads, garbage collector threads, so you are basically time slicing the CPU to either run your application threads or your concurrent threads. So for maximizing throughput, GC needs to be out of the way. So the first thing that we want to do is making sure that marking and compaction can be done together in a stop the world pause. Basically, you want to stop the application, quickly finish your pause, and then resume the application. And the problem of fragmentation can thus be avoided. And the second one is to have the concurrent work as much as possible. And if you avoid that concurrent work, then your applications are not starving for resources. Okay. Next is now with the same block diagram that I had earlier, how would I change this into a throughput maximizing GC? So remember, I mentioned no concurrent work, right? So basically, we take away the concurrent threads, and that's your parallel GC collector right there. So this is a simplistic representation of what the collector does for parallel GC, the throughput collector. But many people have a problem with that, especially when larger heaps and with a lot of mutation to the heap. Many people say that they cannot handle the long pauses. And when that happens, we have to understand the underlying cause. The underlying cause for these long pauses is a full compacting garbage collector. Basically, what's happening is that your entire heap is marked and compacted in one big stop the world pause. Yes, you have parallel threads with the pause within the pause itself, but this single full compacting garbage collector it can have predictable stop the world times, unpredictable stop the world times, and it can cause stalls like for undeterministic period, because depending on how the mutation rates and the promotion rates because of the generation. So here we're talking about how this singular whole heap pause can cause a problem, and it will not scale well with your application. So in order to have some scalability and some predictability, we need to be able to control the unit of work. So how many regions or what is the area that we're going to collect? We need to be able to control that. So this is why the G1's regionalized heap concept was born. So when you have regions, your unit of work can be restricted to just adding one region at a time. And that makes it very, finer control. And then the second concept that G1 introduced was also the partial compaction. So partial compaction is that only do the work as much as is needed based on your pause time goals. And if you can do some of the work in the background, then you can be more latency sensitive. So with those two concepts in mind, let's design a latency sensitive garbage collector. Am I still okay? Can people hear me still? Awesome. All right, thank you. Yeah, okay, awesome, thank you. So here's a latency sensitive collector. I was talking about the generational concept, remember? So we'll keep that, right? Because it helps with throughput. And then I mentioned the parallel work, which I was talking about partial compaction, right? So again, partial compaction helps with keeping your latencies lower, right? And the concurrent, so while with the partial compaction, I also mentioned the concept of regionalized heap, because that's really what is behind the partial compaction. So you can control the amount of work to be done. And then, of course, concurrent marking. So what we see here right now is what, it's like the block diagram for G1 GC. So you have generational, regionalized heap, partial compaction, concurrent marking, and there you have it. That's your G1 garbage collector. But then sometimes, based on your application, and that was the question that Nikita was asking, like, how do we get to low latency collectors being the default? So this is what we are observing with some of the applications. They complain, many of the, developers or people that are running these applications on the JVM, they complain about tail latencies. So it's not about long pauses anymore. G1 solved that problem. So it's about tail latencies. Oh my gosh, some of my customers are getting these tail latencies that are really, really bad. And I'll show you some examples of that. So what we really need, that means we need a predictable, scalable, low latency collector. right? So how do we go from where G1 is to this new low latency collector? We keep the partial compaction because that's one of the things, it gives you finer granularity for collection, but we move it out of the stop the world phase into concurrent phase. So basically, even partial compactions can sometimes blow your pause time goal. That's because, there's like a density of the regions, for example, how much popularity of the live objects in the region. Based on all those things, your prediction logic and your actual pause time can vary a bit. But a low latency collector cannot afford that. So what happens is the low latency collector will actually make that compaction do that compaction concurrently with the application. And then now there may be some phases that have to be stop the world, but make a time budget for them. So basically, if you cannot finish the work in that time budget for the stop the world phase, then you go back to doing concurrent work and then come back to stop the world. So basically, you're doing the work that needs to be done during the stop the world phase concurrently, and then incremental stop the world pauses till the work is done. So sometimes you will see this concurrent marking and mark and back to back because there is a lot of stop the world work that needs to be done. So that was the incremental concurrent work. And then, sometimes you will have to tell the application to back off a bit. So what you can do is tell the application either to have stalls or kind of help with the relocation work of the live objects. So that is called self-healing. So with this in mind, let's design a low latency garbage collector. Okay. So we already talked about generational, regionalized heap, and parallel work. Generation, we already talked about young and old and maintenance barriers. And in parallel work, I just introduced the concept of concurrent marking as well as concurrent compaction. So instead of doing the compaction and stop the world, do it in a compacting concurrent collector way, and also do it incrementally, like in partial, right? So as I mentioned, that marking and compaction can be done incrementally. And I also talked about the concept of self-healing. Of course, both those, anything you do concurrent or anything that has barriers, you need self-healing is done with the value barriers, loaded value barriers. So that is maintenance overhead as well. So basically, what we have designed here is ZGC. The only thing that's missing right now from ZGC is the generational part of it, and they're working on it. The ZGC team is working on the generational part of this. So this is not there yet, the generation right there, but everything else is right there in garbage collector. So this is the block diagram of ZGC. Now let's move to introduction. All right. So what were the design considerations of Z garbage collector? So if I had to define Z garbage collector, I would say it's an adaptive, near real-time, scalable, predictable, low latency collector. So there's just a mouthful of words, right? But what it means is that ZGC adapts to your application. It gives you sub-milliseconds pause time. And that is true. You heard it correctly. It's not 10 milliseconds anymore. It's actually less than 1 millisecond. And I'll show you some examples of how I've tried to break ZGC. And I think I've been successful just one place, and I will show that here too. Predictable, again, predictable means that you have a guarantee that your pause times are going to be less than 1 millisecond. And scalable because you can get heaps from 8 megabytes to 16 terabytes. So these are the points I just mentioned. Sub-millisecond, pause time does not increase with the application, live data set or root set size. Again, your heap can range from 8 megabytes to 16 terabytes. And the concurrent compaction and your concurrent collection kind of has this ability to say that your application throughput is not going to fall below 15%. So every garbage collector has this throughput expectation quota. So, like for example, G1 GC tries to guarantee that application throughput is not going to fall below 10%. Actually, we strive to let it not fall below 5%, actually. And ZGC's guarantee is 15%. So because you're turning more and more towards lower latency guarantees, your throughput kind of suffers a bit with that. So there's two concepts that I want to talk about with respect to ZGC. The first concept is colored pointers. Okay, so if you have an object address space, out of that object address space, ZGC tries to use 4 bits from the unused space for tagging. So basically, from 0 to 43 is your actual literal object, because object address. Remember, I mentioned ZGC can handle up to 16 terabytes, so that's 2 raised to 44 is 16 terabytes right there. And of course, the top is unused, so from 48 to 63 is unused. And there, like I mentioned, 4 different bits. So marked 0, which means the object is known to be marked 0 and 1. So is the object known to be marked? Next comes the remapped. So is object known to be not pointing into the relocation set? And relocation set, the concept is similar to ZGC, where it talks about the collection set. So what are the regions that I'm going to move from the from space to the to space? That's known as the relocation set. Okay. Then comes, and the last thing is finalizable, which means is object reached only through a finalizer. So these things are tag bits that are in this the address space. And to read more about this, please refer Per Ledin's ZGC JFocus presentation, and it's right there. So taking a step back, you're looking at the metadata of of your work. These pointers that we're talking about. It's stored in those 4 bits as shown here. The other thing that you can see that the way ZGC handles this, so we have 4 different bits that talk about 4 different states, and there's handled through virtual mapping. They're also called virtual address tagging. So if you were looking at ZGC concepts and you're looking at garbage collection concepts, so this is covered under virtual address mapping or virtual address tagging. The current implementation that's out there in OpenJDK that you'll find today for x86 64 as well as ARM64 is the use of multi-map. Okay, but you can also, in the past, Spark used to be a processor as well, and you had the actually hardware would assist with these tagging bits. So, but that's not there anymore. So we just have these 2 implementations there. Now, let's talk about these phases. So, what is remapped? What is marked? What does that mean with respect to ZGC? Okay. So let's quickly dive in. So we have garbage collector background threads running here, and your Java application is running along with those background threads. Okay. So what you see here is that you encounter a first stop the world pause. Many of us know this as initial mark. ZGC calls it pause mark start. Okay. And then comes the concurrent map or remap. So during the pause mark start, what we see is that we want to make sure anything that's directly reachable by the routes, right? And there is an enhancement done in JDK 16 where the thread stack scanning which was a part of the pause mark start, is actually moved to the concurrent phases. So now all your the time that was spent in thread stack, which is basically kind of your root set, is now totally not there anymore in the pause. That's why ZGC can achieve sub-millisecond pauses now. The concurrent mark, or the remap, which ZGC calls it, is where ZGC traces the live object graph and marks any non-root objects. And this is where I talked about. I will talk next about the logical striping. This is another core concept of ZGC. It divides the heap into logical stripes. Okay. Then the next phase is the pause mark end. So this is similar to other GC's remark phase, right? And then basically what the application threads, the mutators basically, traverse the objects that are not yet marked. In ZGC case, I was talking about the being time bound, right? So ZGC in JDK 16 tries to cap the time spent in pause mark end to 200 microseconds. So anytime the work goes beyond this, beyond 200 microseconds, then you have to go back to concurrent marking and then have another pause mark end, and so on and so forth till the stop the work that, till all of the unmarked objects are marked through. Okay. Next comes concurrent prepare for relocation. And that's very, very simple. Basically, a relocation set, as I mentioned, is similar to your collection set. And it kind of helps with incremental compaction, right? So you only relocate certain regions. And during this concurrent preparation phase, ZGC identifies like the regions that will be utilized for this movement from the from space to the to space. Okay. And you also, if you remember, like what GC work needs to be done, there's like the weak roots, the non-strong references, class unloading. All this is done concurrently in ZGC, and that's done during this concurrent prepare for relocation phase. The last phase is pause, relocate, start. And that is basically what you know as it's a stop the world phase, and it's movement from the from space to the to space, but kind of in the stop the world fashion. So this is where anything leftover metadata and methods that are kind of moved. Previously, prior to JDK 16, the stack scanning was also part of this phase, but now that has moved to concurrent phase. So this pause is really small, it's sub-milliseconds. And the final phase is the concurrent relocate, where ZGC actually does the work of moving from space to the to space. And what happens here is that we use the load barriers to detect any colored pointers. Remember, we introduced the concept of colored pointers. So the load barriers will see in what phase it is, and then that's where it moves. So that's basically what are the total phases of ZGC. And now let's look at concurrent marking, just a little bit details with respect to the striping that I mentioned. So here's your heap, okay? And your GC threads from 0 to n, okay? So based on the count of your GC threads, your heap is actually divided into these logical stripes, okay? And so what you can see, I have logical stripes from 0 to n, and again 0 to n, and 0 to n. So that is kind of the work that you do with respect to your logical stripes. And you can see right here next. So GC thread 0 only deals with stripe 0. GC thread 1 will deal with stripe 1, and so on and so forth. And then they'll keep on doing as they have this entire heap structure laid out. Okay. So what does concurrent marking do? During concurrent marking, your heap will be divided into logical stripes. Each GC thread kind of works on its own stripe to make sure that you are minimizing any kind of interactions between shared states and stuff like that. So you work on your own time slice, heap slice. There is load barriers to detect loads of non-marked objects. So if the objects are not marked and they're being loaded, then you have to make sure that the barrier takes care of sanitization. And as I mentioned, reference processing is done concurrently during the concurrent marking phase. This also helps. There's a concept of thread local handshakes that is done in the stop the world phase, and I will cover those shortly. Okay, but first let's talk about the barriers. So the concept, the barriers are basically loaded value barriers or loaded reference barriers. So you would hear the concept of LDB or LRB. And in the simplest way to talk about these barriers, I would say you're basically updating from a bad reference to a good reference. That's the simplest thing that the barrier is trying to do. As I mentioned, these barriers can be self-healing when updating the source memory location. Basically, what I'm talking about here is that you have the concept, you have the understanding of not only the reference value, but also have access to the memory address. So why not just do repair the address as you go forward, okay? The two things to remember are these two-space invariants. So basically, these are the guarantees that the garbage collector provides. All visible loaded references, basically all references that can be seen by the loaded references that can be seen by the GC will be safely marked through. So that's a guarantee that the GC provide. Okay, so the collector will take care of that. And then the second thing is at any given time, anything that's visible to the garbage collector and it's loaded, is going to be pointing to a safely accessible location. So remember, any given time that you see any loaded reference, you will make it is guaranteeing the GC guarantees that it will be pointing to a safely accessible location. Okay, so those two guarantees are what make up the ZGC invariants, and the concept of these invariants is actually covered very nicely in the C4 continuously concurrent compacting collector paper. So if you want to read more about that, please download the paper and kind of read it through. So now that we understand barriers, let's talk about the concept of concurrent compaction, right? So how do we achieve concurrent compactions thanks to these barriers? So the load barriers or loaded reference barriers or loaded value barriers are used to detect objects that are pointing into the collection set. So first, remember I mentioned the concept of relocation set and collection set. They're the same thing. So I want to move objects in the regions in these collection set from the from space to the to space. So I employ load barriers to detect any objects that are object pointers. Okay, as I mentioned, it can be self-healing because we have the reference value and the memory address as well. What ZGC does, it employs off-heap forwarding tables. So if you remember, if you know about other garbage collectors, you have the forwarding address in the header, right? But ZGC doesn't deal with that. It actually deals with something known as forwarding tables, and they're not stored on the heap. So having these off-heap forwarding tables actually enables ZGC to be immediately released and reuse the virtual space. Virtual and physical memory, actually. So let's now, with the concepts out of the way, let's look at how ZGC became production ready. So in JDK 11, when it was introduced, it was experimental. So in JDK 15, ZGC is now production ready. So how did ZGC do this journey? So even before JDK 11, ZGC introduced the concept of thread local handshakes, and I will talk about it shortly. With its introduction as experimental garbage collector in 11, it introduced the concepts of load barriers and colored pointers in OpenJDK hotspot. It also does concurrent reference processing. That was done in JDK 11. Concurrent class unloading done in JDK 12. Uncommit unused memory, JDK 13, and compressed class pointers. So one of the things that you would have noticed to be able to access 16 terabytes, the concept of compressed OOPs are no longer they're possible, right? So, but in JDK 15, you can at least get compressed class pointers. So that's a big achievement with respect to ZGC improving its footprint a bit. So here is what I call the difference between thread local handshakes. Oops, sorry, let me go back. And global stop the world. So prior to this thread local handshakes and their introduction in JDK 10, you would see something, and I will use my pointer right here. You would see something like this, okay? So your application threads come to a halt here with the save point when the save point is requested. Sorry, actually, and I mean, if it's requested right here, it still needs to complete some work, so it will continue like that. So by the time all the threads come to a halt right here, this time is, so to speak, time to save point. Basically, the GC threads are waiting for the application threads, all of the application threads to halt, because they're checking a global space to make sure that they all come to a halt. And then GC threads start their work. Right here, GC threads complete their work, and then the application threads can resume. With thread local handshakes, actually, the save point is requested here, but what happens is, say, you're the first application thread. Right here, this is called a thread local handshake. So basically, anytime that you need the mark stack information or any kind of information that you need from the application threads, that's what the information is exchanged. The GC can start doing its work with that information, as well as the application thread can resume. So basically, as you can see, the handshakes are basically thread local. Each one does its own, so they have a thread local check that they do, and it kind of helps with that concept where we can save time in the stop the world phase. So because you're now handling each thread by itself, there is some maintenance overhead, because remember, now it's not the global check that you have to do for, all threads do the check, but you have to request it individually for each thread. But it provides a lot of time savings with respect to the pause itself. Finally, going to the performance impact. I think my slides were trying to get to there faster than I was, but now we're here. Let's talk about the benchmarks that I'm using and the scenarios that I've designed to kind of show you how ZGC kind of balances itself, okay? So the first one I want to talk about is fragmentation. So how does ZGC handle fragmentation? The way I've kind of got this benchmarks to get me the numbers is I have made the live data set, LDS, very large. So it's 50% of the heap size. What I also have done is I have given it varying object sizes. So having those, in G1's case, there's the concept of humongous objects that have to be allocated out of the old generation. And I've also given very high allocation rates to the application. So this is my test configuration. I'm using an ARM64 system that's running Linux, JDK version 16, early access build. I'm using the benchmark called HeapFragger. There's a link to HeapFragger right there. It's a benchmark designed by Gil Tenney of Azul Systems. And please go ahead and look at that. The link is to the source GitHub repo. There's this additional thing, because I'm using 200 gigs of heap space, and I was running this benchmark, so I wanted to use large pages, which kind of helps with the data structures and the heap, the paging. It kind of minimizes the paging effects and stuff like that. So always speed touch is also a good option for large pages. For larger heaps, basically. So as I mentioned, my initial and max heap size is 200 gigs. Live data set is 100 gigs. And I test both ZGC and G1GC. Allocation rates 1 gigabytes per second, and my object sizes are anywhere from 128 bytes to 32 plus megabytes. I went 32 because I want to, when you have humongous objects in G1GC, if they span more than your heap region size, G1 has 32 megs as the largest region it can offer, then those become contiguous regions next to each other. They're allocated out of contiguous regions. So I wanted to make sure that I'm exploiting that fact so that let's see how it handles these fragmentation, because this can lead to a lot of fragmentation. Okay. So here is a chart, and in the reference section, I have provided information on how I've, what tools I've used for these charts. Here you see a chart that is generated by Sensum. So Sensum is a parser and a plotter script by JClarity, who were acquired by Microsoft. And we're trying to make sure that the parsers are open sourced soon enough. So we're working on that. But what Sensum helps me with is kind of provide you a visual impact of what the allocation rates look like. So again, going back to my laser pointer, what you see right here is your kind of initialization phase of your application, and you can see it in the promotion too. So these allocations and then these promotions kind of help with your live data set, kind of building up of your live data set. So you can think of it as a cache, a high hit rate cache, right? And then eventually over time, what you can see is it's a steady rate, because I mentioned about 1 gigabytes per second. You can see right there, and it's allocating at a steady rate right there. And that is all that I was asking from the application. And as you can see, the promotions are basically it's doing transactions with your cache that you built up. Okay. Let's go next here. Let's look at the same thing, but from ZGC point of view, as well as from the application point of view. So as you can see, sorry. Hello? Yes. Okay. There's a little bit of slides to cover. Should I continue that, or do we still want me to join the other link? Hello? Can I continue the presentation, or do you want me to stop the presentation and go to the discussion zone right now? Okay, thank you. Okay, so as I was saying, so this particular application right here on the left, you can see the worst case pause time that is observed by ZGC is it's almost 0.55 milliseconds. So again, less than 1 millisecond. But because ZGC had to maintain its sub-millisecond pause time goal, your application did see some stalls. And those stalls are 350 milliseconds. So ZGC does the background work, and sometimes it can introduce stalls in the application. But it's not as bad as G1, as I will show you next. So the same application, when running with G1GC with the default pause time goal of 200 milliseconds, you can see the latencies that the application observed. And as you can see, it's 9 seconds, 9.5 seconds actually right here, 9.5 seconds. And this was where the application that was running ZGC, it only saw about 300 milliseconds. So the reason is simple. G1 will do its best to reach your target pause time goal and not try to exceed it. But again, if I'm doing it, if there's a lot of fragmentation on the heap, G1 does encounter two-space exhaustions, and then it tries to recover back the fragmented heap. And because I was doing these kind of short-lived humongous objects for G1, I kind of handicapped it and trying to break it but it did not do any full garbage collections. It did a lot of mixed and lots of two-space reclamations, and that's how the tail latencies are. So this is what people mean by the tail latency. So the application can see it has really high tail latencies. In G1's cases, the tail latency is not that high. So this is where if your application is observing this, you will move to ZGC and kind of get the guarantee of sub-millisecond pause times for the garbage collector itself. Now, there was one case of fragmentation. What I want to see is that if I have large objects and higher allocation rates, how does ZGC adjust to these this kind of variability? So test configuration is the similar system, same JDK version, but I'm using something called hyperallocate, which is a benchmark by the AWS Corretto team. Again, everything else is pretty much similar, similar size LDS and the benchmark threads. Object sizes are similar too. This is how ZGC, when it's under pressure, where you have high allocation rates and short-lived objects, it looks like that. So at mark start, this is the what your liveness looked like, right? Because you're just going to start marking. And then after the marking, after the concurrent phase is done, relocation is done. At the end of relocation, you have reclaimed back the heap space. So these were all your transients, right? And you have reclaimed back this. This is your live data now. So remember, I mentioned the live data set is 50% of your heap. So 100 gigs is live, and that's what you see here. So ZGC does a great job of reclaiming back, most of the dead objects, and it kind of maintains that. This is exactly what we wanted to see. Now let's go look behind the scenes. How did ZGC achieve that? Okay, so right here, you can see some interesting chart. What I've done here is I want to show what are the different reasons for triggering a garbage collector in ZGC. So let's look at this table right here. The first one I'm going to talk about is the timer. So when there is no other GC being performed, there is this kind of timer-based. So when the timer is up, do a garbage collection cycle. When the timer is up, do a garbage collection cycle. Then the next one is something called warm-up. So you're basically warming up your garbage collector to start doing garbage collection cycles. And that is based on your heap occupancy threshold. So basically, is it 10%, 20, 30? If there's no other garbage collection being done, then let's warm up the collector and start collecting. Let's get ahead of the game, so to speak. The next one is called allocation rate. And that is basically, if your application is having high allocations, then you could possibly run out of heap space. So start a garbage collection for ZGC if you observe high allocation rate. Okay, allocation stall. Now, this is what you want to avoid. Basically, the reason you want to avoid that is in order to guarantee sub-millisecond pause times, you need to be able to ask the application threads to back out. So basically, you're blocking your application threads because you don't have any more space to allocate, because the ZGC needs to do its work, needs to keep up with the allocation rate, right? The next reason is called proactive. So if ZGC sees that the allocation is getting higher, crossing a boundary from basically the occupancy of the heap is getting higher from the last GC cycle, like 10% higher, then it will start this proactive collection. It's either that or 5 minutes have passed since the last cycle, then it'll start the proactive collection. And then finally, it's high utilization. If your heap has high utilization already, but the allocation rate is low, then ZGC can avoid any allocation rate stall. So basically, timer, warm-up, proactive, high utilization, allocation rate, and then finally allocation stall. So basically, this is the priority that we want to be, so we can avoid allocation stalls. But because my application, I kind of purposely made it to try to break ZGC, right? So what you see right here is my application sees basically a lot of allocation stalls right here. All this blue is allocation stalls, and then only a teeny tiny allocation rate. So basically, I've managed to kind of try to break, do the most expensive garbage collection cycles in ZGC, which are the allocation rate and allocation stalls. And let's see how ZGC handled it. So this is a very high allocation rate application, and my worst case pauses are just 2.1 milliseconds. So yes, I did manage to break the collector away from its 1 millisecond pause into 2 milliseconds and that's marked start. And that's because it still had to do a lot of work with respect to this high allocation, and sometimes because of the stall itself, right? So I have introduced some stalls early on because of the high allocation rate. How did my application see it, right? So the same benchmark from the benchmark point of view, you see that the application sees the worst case. Oops, sorry. The application sees a worst case of less than 130 milliseconds. So less than 130 milliseconds. So although ZGC had a lot of application stalls, but the worst case latency that the application could view was less than 130 milliseconds. And now let's see how G1GC do. So this is basically a GC Hyster chart. Basically, it's a parser, and then you plot it in GC Hyster. What you see is a lot of two-space exhaustions right here. These are all two-space exhaustions and remark pauses that are like just incrementally bad. And if I compare that to my application, what you can see here is my application also views the pauses just as the garbage collector views it. So basically, the application right here. So the worst pause for the GC was about 1.2 seconds, and the application, the worst pause was about little over 1.2 seconds. Okay. Next, of course, I'm just trying to get the scaling right. Now let's compare CGC to G1GC. I am just going to let you guess for the same application and the same stress parameters which one of the chart is ZGC and which one is G1, because we just talked about this. So same application, G1 lets the application stalls as high as 1.2 seconds, whereas G1GC doesn't even cross 200. So it's less than 200 milliseconds. And that's the guarantee that a low latency garbage collector can provide to your application. This is, again, remember, I have contrived and I've kind of trying to break the collectors, and still they all are doing really, really good job. And so this is the state of the garbage collectors today in OpenJDK hotspot. So please feel free to try these. If you see high tail latencies in your application, try ZGC today and get the latest one, early access, so that you can get the sub-millisecond pause times that I've shown here. This is a link to the references and the tools, and I thank you. This is from the Java team at Microsoft, and thank you very much for your time.
Oh, thank you, Monica. You did it in spite of technical problems. We have not so much time for questions, but we have them. And can you compare in last minute ZGC with Shenandoah? Is there any advantages in ZGC over Shenandoah?
Shenandoah now has evolved and is much better than when it initially was introduced as an experimental collector. So I'm going to quickly talk about, we talked about the marking, right? So Shenandoah's marking is a little different because it employs similar marking concept to G1 GC, which is snapshot at the beginning. Shenandoah also has the forwarding pointer now in the header. So previously Shenandoah had the Brooks style pointers, but so you had a lot of overhead because you basically had to dereference every time.
Monica, we have no time, so continue in discussion zone. Thank you very much, and
absolutely.
thank you.
Thank you.